Okay, so welcome everyone to the last talk of the fourth season of the Isogeny Club. Before we introduce today's mystery guest, we actually have another surprise for you all, and it is my great pleasure to introduce the new Isogeny Club co-host, Maria Corterial Santos. So yeah, welcome Maria, and please take it from here.
Yeah, thanks for the introduction and for you and Krijn for inviting me to be the new co-host. So today I'm very excited to present our speaker, who is not so mysterious anymore. It's Krijn from Radboud University, who many of you will better know for being the former co-host of the Isogeny Club. And today he will present Return of the Kummer. So Krijn, take it away.
Yeah, thank you. Thanks to the organizers for inviting me. So today, actually, it's a bit of a special day for me because it's the 25th talk of the Isogeny Club. And also, so I will switch from role from here on. So I'm very happy to be able to present Return of the Kummer as a sort of goodbye. And in a totally not an act of nepotism, this is also a joint work with Maria. So yeah. Anyway, what I will do today actually is I will start off with a bit of an explanation on Kummer surfaces and so hyperelliptic curves as well. So if you know these objects very well, then actually you can take it, I don't know, you can get some coffee for the first 15 minutes or so, but it's just to sort of get a sort of common language for these objects. And then we'll see what we're actually going to do with this in this sort of isogeny-based cryptography, because it is the Isogeny Club after all. So the first 15 minutes really is quite low level. And also if you've I don't know, if you come from a background of crypto engineering and you've never seen this sort of algebraic geometry in the back, this is really this is really what I'm trying to get across. So let's start with this picture. You all know this picture. This is an elliptic curve, and usually you notice with these lines on it that define an addition. And then when we teach this to, I don't know, students in an intro to crypto course, they really actually never really complain about this. They will just see that object, and then they'll most often will go, okay, this is some kind of group structure on there, fine. But if you think about it, that's actually very, very weird, that if you cut out a curve geometrically, then you get an addition on there. And that's because we have two objects going on here, right? So we have the points on the curve that satisfy this equation, but we also have this addition that is going on in the Pigara group. And that's really like this sort of, for a curve, you get this Jacobian there. And the arithmetic really is coming from the Jacobian. Then on top of that, in cryptography, we don't even work with actual points on this curve, but really we work only with this Kummer line, with this X-only arithmetic. And there you're just working with essentially one value, usually projectively. And now, why I'm trying to go over this, that's because in genus 1, these objects are, right, isomorphic. The curve is isomorphic to its Jacobian. And working with just the X-coordinate doesn't feel like a different mathematical object. It just really feels like a sort of a trick to reduce complexity. But then if you have this sort of intuition and you move to genus 2, it doesn't really hold anymore. In genus 2, these things become separated. And so you actually need to sort of think of these points on different levels. So on the top level, we have this set of points on a given curve. Then in the middle, there's this Jacobian. And actually, when you define this Jacobian as they do in, I don't know, Silverman or in the Prolegomena, you get these divisors and you're working with these divisors. And then on the bottom level is this Kummer line, which is formally it's the Jacobian and then divided out by the involution. But for us in genus 1 case, you can just think of the projective line. And because it's a line, it doesn't even feel like it's a different object, right? Like it's a variety. It just feels like a value. But luckily in genus 2, this is slightly more complicated, right? So on the genus 2, the curve is a slightly higher degree object. But then the Jacobian is also still these divisors, but the Kummer becomes a surface. And in genus 2, it will become a surface in B3. And it looks a bit like that drawing right there. And that's actually where I'm trying to get through. I want to get through how are we going to do cryptography on these Kummer surfaces, because it corresponds naturally to this X-only arithmetic on elliptic curves. And how is that associated actually to this curve that is lying above there? Because you can also do this sort of cryptography by just working from these theta structures and so on. And this really gives you, like we know from the 2-2 isogenies work, this gives you fast tools to do these things. But for me, it's more naturally to come from this from a curve perspective. But these two things really end up somewhat in the same object over there in the middle. So I'll do this in 3 stages. First, I'll go over these Kummer surfaces and where do they come from and how do we see them in cryptography, and how do we see them in pre-quantum cryptography already, but also how are we going to use them in post-quantum cryptography. Then in the second part, we'll go over actually a very general construction that allows you to translate things from genus 1 to genus 2. And that's where we started this project with Maria, because what we thought was, as a sort of ridiculous hobby project, what if we apply this trick to SQIsign verification? Is that actually doable? And you might wonder, why would you want to do that? And we'll get to that later, but we thought it was interesting and there was good reason for it. And then in the third section, actually, we had to solve a lot of problems that we had in the second section using pairings. And this really gave us a new idea on how to, for me personally, how to think on these pairings. So I wanted to explain this to you, and then you'll also see how that will help us solve things in the second section. So let's start with the Kummer surfaces. So our starting point is this genus 2 hyperelliptic curve, right? In this general form, you just get y squared is fx for some polynomial, and it will be of degree 5 or 6. And then what's the difference? Well, how can you interpret these curves? If it's degree 5, right, and you think of like a generalization of an elliptic curve, you have these 5 points that cross the y-axis, and we call these the Weierstrass points. And we have a single point at infinity, but it somewhat, also crosses the y-axis. Whereas in degree 6, you have these 6 points crossing the y-axis already in the affine part, and then at infinity you get 2 values of infinity. And you'll see that this difference between these two curves, curve shapes, will show up in other parts as well, but usually you can translate back between these two forms, right? Similarly, as you can do in a genus 1 case. So if you have a rational point on your curve where your degree of f is 6, well, you can translate it to put that rational point at infinity and get a degree 5 model, and vice versa. Now, there's also a much more special model actually that we'll need in this talk, which is the Rosenheim form of a hyperelliptic curve. And that's when it can be written as this form that you see over there, where lambda, mu, and nu are the Rosenheim invariants. And then not all curves have this, are not all isomorphic over the base field to a Rosenheim form. But sometimes when you have enough rational 2 torsion, I think if the 2 torsion is rational, then you can define this sort of Möbius transform, which puts some of the 2 torsion, I'm saying 2 torsion, probably it's going to be the Weierstrass point, which puts some of these at 0, 1, and infinity, and maps the others to lambda, mu, and nu. And that gives you exactly this isomorphism that we are looking for to put a curve into Rosenheim form. And you'll see actually later on that this will be very important when we go to Kummer surfaces. And then we need to go actually to this Jacobian, because we cannot do anything yet on this hyperelliptic curve. There is no group structure there. But we said before, there is group structure on the Jacobian. So what is the Jacobian here? Well, one way to think of it, modulo a lot of remarks, but to think of it, you just take 2 different points on C, and then you map them to the divisor P1 plus P2 minus D infinity. And D infinity is the generalization of this point at infinity on the elliptic curve. In this case, it will be a divisor. And what will this divisor be? Well, in this degree 5 case, you needed 2 times the single point that you had at infinity. Whereas in this degree 6 case, you just take those 2 points at infinity separately. And then how do we do arithmetic on this Jacobian then? Well, we keep, when we want to add 2 of these objects in the Jacobian together, we sort of want to represent them again as, maybe R1 plus R2 minus D infinity. But if we want to implement this on a computer, we have to represent these in some way that makes it easier to work with. And this is a Mumford representation. So if you had this element of Jacobian P1 plus P2, I'm skipping the d infinity here because you can usually ignore this with some special remarks. Then P1 and P2, you can give these as in the coordinates of your curve, right? X1 and Y1, and X2, Y2. And then you get these Mumford representations, which are two polynomials A and B. And A is exactly the roots X1 and X2, and B will exactly evaluate to Y1 and Y2. Now, if you do this for d infinity, we represent it as 1, 0. And then there's a thing going on with this Galois invariance where similar to, no, that comes a bit later. So these elements of the Jacobian are not just these pairs of points from C with X1 and X2 in your base field, but if you have a small field extension, they can still lie on your Jacobian. So let's say I want to look at points in the Jacobian over FP. I can also get points on the curve over FP squared, but then I need both of those points under the Galois invariance. So you get, for example, I and 3 minus I and minus I and 3 plus I. This is still a sort of a rational point on a rational element of my Jacobian, even though the points themselves are defined in the field extension. And this is convenient because if you look at the Mumford representation of that divisor, that Mumford representation is actually defined over K. So that really does make sense. And if you're thinking now, this looks a bit like how we defined kernels of an isogeny to be rational, even though the kernel generator might not be. That's exactly what you should be thinking of, yes, because you would get that the kernel polynomial would be defined over FP, similar to how this Mumford representation would be defined over K, say. Now, if we have such a Mumford representation for two divisors, there is an algorithm by Cantor that really computes the third divisor, this dr. And so this allows us to add points and to do scalar multiplication on this Jacobian. But for practical things, it's actually quite slow. And this is why we want to move to the Kummer surface, because we'll see that things will speed up quite a bit when we get to there. Now, this Cantor actually, when I first read it, and I think for the first few months that I was working with it, I always thought it was the other Cantor. But as you see it from the citation, this is not the case. This is David Cantor, and he was from he did his work in the 1990s. And so he really deserves to get, I think, his name more well known so that people don't make this same mistake of thinking it's the other Cantor. Okay, so how does this, can we also do this sort of interpretation of this Cantor's algorithm with lines on a curve? And it turns out that, yes, you can do this. So if you have the divisor dp and it corresponds to P1 and P2 on the curve, and similarly for Q1 and Q2, you can again draw a sort of higher degree function through these points, and they would intersect your curve in two other places. And from there, you again sort of switch, how do you say this? You mirror in the y-axis, and you get your R1 and R2. And this really often helps me in thinking on what things are going to happen on this curve. For example, if you're thinking of what would be the elements of order 2 on a Jacobian, this sort of interpretation of the curve is going to make more sense, because in the genus 1 case, you know that's these points where it crosses the y-axis. And with this addition in mind, actually, that would also make sense if we take two of those, right? So if we take P1 and P2 both to be these Weierstrass points, then this geometric interpretation says that if we mirror these, we end up at infinity. And indeed, then you can actually check that these sort of points map to the elements of order 2. And then actually, well, we saw that we had 6 of these points. So if we just take 2 of these and we have 6 of them, then we get 15 options for them. So the elements of order 2 will be these pairs of Weierstrass points, W1, W2, or W3, W4, and so on. And in Mumford representation, we can write that as these Lij's. And really, the left-hand side will just be the polynomial with these roots, Wi and Wj. And the right-hand side, well, the y value is going to be 0 for both of these. So this polynomial is just going to be 0. And then we get our structure of the 2 torsion on this Jacobian already. It's going to be z mod 2 to the power of 4. And that will actually be very important later on, because this 2 torsion really tells us a lot about how these two isogenies are going to work as well. And a lot of the tricks that we will see with pairing really rely on the structure of this 2 torsion. And then you might actually now already see why this Rosenheim form was so important. So if the Rosenheim form says that all of these wire stress points are rational, then also this 2 torsion will be completely rational. And that's really what we want. That's what we want to work with. Now, how do we get to this Kummer? We started out with these elements of the Jacobian, but now we are going to divide out by the involution. So minus this element becomes the same as this element itself on the Kummer. And by some kind of magic, this really becomes a surface in P3. And the equations are on the right, and it's really not very clear from how I wrote it here, because the equations get kind of big, but still it's just a single equation where you have 4 variables, x1, x2, x3, x4, and then 3 polynomials, k0, k1, and k2. And these polynomials, k0, k1, and k2 are in these variables, x1, x2, x3. And then your elements really are these points x1, x2, x3, x4 that satisfy this equation. And they are then defined up to a scalar, of course, because we're working in a projective space. And now, similarly as we can do on the genus 1 case, it means that we can do this scalar multiplication. We can still do that on this Kummer surface, right? We don't get a group structure there, but we get this sort of pseudo group structure. And you may remember, actually, for doing things like Diffie-Hellman, this is usually already enough. And maybe you can think how far we get to do isogeny-based cryptography using just this Kummer surface. Do we actually need that much from the Jacobian? Or can we do a lot of these tricks already on the Kummer? This is how it actually looks if you take the affine part of it. And it's a bit of a famous object, I think. I know that we had one of these printed out in our mathematics department, I think because algebraic geometers really love this object. And one of them told me that, sorry, it should be errors coming in here, that these points over there where it sort of fits together, that these are the points of order 2, which is a nice geometric interpretation of this fact. So on the bottom right, you see 2 examples of points on this Kummer surface. So the point at infinity that we had, that is the 0 element on the Jacobian that we had, maps to the 0 element on the Kummer surface, and it just maps to 0, 0, 0, 1. And these points of order 2 that we had on the Jacobian, they map to what I will call dij by some formula. And in general, we can easily map from the Jacobian to the Kummer. I left this out of the slides over here, but just trust me, it will become some formula like we see over here, where it's 1 wi plus wj, wi times wj, and then some gamma that makes sure that it fits this equation. Okay, so now we have this curve, we have the Jacobian, and we have the Kummer surface, and we know how to go from the curve to the Jacobian by selecting 2 points or so. We also know how to go from the Jacobian to the Kummer surface. Now, there's a bit of a warning here, because the construction so far assumes a general curve, and it constructs the general Kummer surface. And this general Kummer surface is mathematically, I think, quite elegant, and it always exists for any curve that you will pick. And it's really well described by the Cassels and Flynn book, the Prolegomena, which is in the bottom left corner in the citations if you need it. They really do a very splendid job of explaining a lot of these mathematical facts and how to work with it. But the disadvantage is it's still not fast enough. Even though it's a Kummer surface, it's not fast enough for what we're going to try to do. This is where this Rosenheim form comes in, because the zoo of these Kummer surfaces is actually a bit broader. So for a general curve, we could construct, well, the curve in the Jacobian and this general Kummer surface. But if we can map it to a Rosenheim form, well, for a curve in Rosenheim form, we can still construct a Jacobian, but then we can make more than just a general Kummer surface. We can also make the canonical and the squared Kummer surface. So the general Kummer surface was this one introduced by Cassels and Flynn. But the canonical Kummer surface was introduced by the Chudnovsky brothers and introduced by Gaudry to do very fast genus 2 arithmetic. As you can see over here, the equation looks a bit more difficult.
Felice di conoscerti. conoscerti.
I think there is some audio, but it's probably not a question. And otherwise, please interrupt me. So this canonical Kummer surface was introduced and used by Gaudry, and it's already quite fast. And then there is the squared Kummer surface, which is a sort of adapted canonical Kummer surface, which was introduced by Bernstein, which looks a lot like it, but the squares are changed a bit. And this is really where you get this sort of the highest speed cryptography. This is the object that we actually want to work with, because for us, the scalar multiplications and so on will be fastest. But remember that we can only work on this squared Kummer surface when we actually have our curve isomorphic to something in Rosenheim form. Okay, so now how were these objects actually already used in cryptography before? There's actually quite a lot of literature, so I don't think I will be able to go over all of it, but I hope to highlight some of the significant things, and in particular the ones that I read that really helped me on this topic. So the first thing is pre-quantum, right? It's the hyperelliptic curve Diffie-Hellman. Now this was sketched already in the 1980s, which is very surprising, and then picked up later by Gaudry, I think in 2004, and really with a very good explanation on how all of these separate operations would work and what the cost would be, and then later on improved by Bernstein and many others. And then actually there's a version in 2014 called Kummer Strikes Back, where these operations are sort of hyper optimized on a very low level by using parallelization only available for Kummer arithmetic. And this by, I'm not going to pronounce all of the authors' names because I'm afraid that I would mess it up, but you probably know the names as well. The tools that they give us, that these works give us, really allow us to do very fast doubling and differential addition on Kummer surfaces. So this is really our starting point if we're going to do operations on this Kummer itself. Now, we then get to isogeny-based cryptography with Kummers. And actually doing isogenies on abelian varieties, there's a lot of works by Costello, Lubitsch, and Robert. And actually really, I couldn't really pick out a specific one because there are just a lot of I mean, there's a lot of literature here since the 2010s. So I put Robert's page there and just check this for quite a lot of works that will guide you through these isogenies on abelian varieties. And then from a different perspective, actually by Costello in 2018, which we'll go dive into a bit more later. And then recently we had this interest coming from this higher dimensional perspective. For example, we know that the SIDH break really relied on computing 2-2 isogenies. And then we had this work recently by D'Artois, Meinl, Pope, and Robert on how you can get very fast 2n-to-n isogenies between theta structures. And in the genus 2 case sort of matches up to this Kummer surface. Really, these are two perspectives on the same object, either coming from the curve perspective or coming from theta models for level 2. The goal here is really to do cryptography on higher dimensional abelian varieties. So computing a 2n-to-n isogeny between products of curves was this first work, whereas Craig really wanted to simulate SIDH on Kummers. And these already give us these tools, these works give us the tools to do fast 2-2 isogenies on Kummers. And then you might wonder, okay, what's left then? Well, this is this is our starting point. We want to do some more advanced protocols on Kummer surfaces. So we have the tools for Kummer arithmetic and for Kummer isogenies. So we can do very long 2n-to-n isogenies. Is that enough to do SQIsign verification, for example, on Kummer surfaces, or not? Do you need more tools there? So our goal is to develop these tools, and for this we need to develop tools for point sampling and 3-point ladders and so on, faster isogenies, and this will allow us to do full SQIsign verification only on these Kummer surfaces. Now our hope is that this parallelization that I mentioned from the first work is also, which is also available for this isogeny-based stuff, allows us to actually speed up SQIsign verification compared to when you're doing it over elliptic curves. Now, this is really a hope because the work that we are presenting now with Maria really develops a lot of the theory, but we haven't implemented it on this low-level parallelization, vectorization level, which is something that we hope to do in the future. Okay, so that was this first part on Kummer surfaces. And now let's see why why it makes sense to use these maybe in cryptography, or what was this perspective from Costello to do SIDH on Kummer surfaces? Where does this arise from? And so our running example, as I mentioned before, is this SQIsign verification using Kummers, and we'll develop some tools for that. But I want to mention this as well, that these tools are more general, of course. They really meant as general tools that allow you to do cryptography on Kummer surfaces in Genus 2, but specifically developed with SQIsign in mind. So where do we start out with? Well, there's something very interesting going on, which is called Scholten's construction, which says that any elliptic curve E alpha over FP squared has a genus 2 Jacobian friend, J alpha, let's call it, over FP. And this is 2 isogenies. And E alpha, what I mean here is an elliptic curve y squared with x minus alpha and x minus 1 over alpha. And alpha has to be an FP2 value, and particularly you cannot have both. Alpha 0 cannot be 0 and alpha 1 cannot be 0. And this is sort of a strange result when you think about it. But there are two interpretations of this that make it somewhat more sensible. So the first, and this was the original point of view, is that you take the Weyl section of this elliptic curve. And this really means doing this sort of the silly thing where you write out everything as you write out x as x0 plus I x1, and same for y, and same for all the variables. And you write this out and you get one equation for the imaginary part and one equation for the real part. Well, then separately, these also define a variety called the Weyl restriction. But really, in reality, it's essentially the same sort of, it feels like the same thing as this elliptic curve, right? Well, what Scholten did was to construct a very specific hyperelliptic curve, C alpha, that he derived from these alpha 0 and alpha 1. And this hyperelliptic curve would still be over FP. And then he was able to define a 2-2 isogeny between this Weyl restriction and this Jacobian of C alpha. And that would make it possible to do everything over FP, because then the elements of your Jacobian are really elements over FP, but they somehow correspond to these points on your elliptic curve E alpha over FP squared. Now, a more rephrased point of view that some of you may be aware of is this terminology of gluing and splitting, where you could say, I said here that the Weyl restriction is a specific sort of gluing. What I mean by that is that you can glue E alpha and the conjugate of E alpha, this product of elliptic curves, along the right 2 torsion. And that will give you this map eta as well to this Jacobian J alpha. Now here, this would be defined over FP squared, and then you have to sort of go down to the FP part, the rational part of J alpha. How does that work actually when you're, why does that help us in doing this, in this Kummer surface-based cryptography? Well, what we're going to do is we take an elliptic curve over FP squared, and we'll take the Weyl restriction of it over FP. Then we get this, we can construct this C alpha by reordering essentially the roots. And then we get this map eta to J alpha. Now, what we first want to do is map C alpha to the Rosenheim form. And we can actually do this, and you can show that this is always possible. Because then what we get is this J of the Rosenheim form. And there we actually know that we can get this squared Kummer surface that we actually want to work with in the end. Right? So we could also construct a Kummer surface for J alpha, the general one. But we want to get this sort of very fast arithmetic going on. So we need a squared Kummer surface, which we get from a Rosenheim form. And then we get this sort of path from E alpha all the way down to this Kummer surface K squared. And this is actually then a sort of a Kummer surface associated to E alpha, but the Kummer surface is over FP. And what we will see is that we can do a lot of stuff that we were originally doing for E alpha. We can do that as well for this Kummer surface K. Now, for the remaining slides, this was the look under the hood. And you can actually just ignore all of this and just think of the first curve E alpha, and there is some map, somewhat of a 2-2 isogeny to K alpha, which we define as this squared Kummer surface. And that's all that we really need to think of for now. So rephrasing this, we get that any elliptic curve E alpha has a 2-2 isogenous Kummer friend K alpha. And actually, what Costello observed is very interesting. It says that it's actually a bit deeper than this. because our original point E alpha has 3 2 isogenies that we know that are rational, because we have this rational 2 torsion P0, P alpha, and P1 over alpha. And it turns out that this Kummer surface K alpha has similarly corresponding 2 2 isogenies, which you can also similarly describe by single points P0 prime, P alpha prime, and P1 over alpha prime on the Kummer surface. Usually for isogenies, maybe you notice for 2 2 isogenies, you need specific subgroups, but in this case, we can actually work with the single points and identify subgroups with them. And so if we have a point of order 2n on K alpha prime, we can also do a sort of a 2n to n isogeny on the Kummers, because we can do that in steps of 2 at a time. And then so the surprising part is that these sort of match up. If I do a 2 isogeny on the level of elliptic curves, it will match up to the same 2 2 isogeny on the Kummers somewhat. So now imagine that I start out with a point P of order 2n plus 2 on E alpha, and I map this down to this Kummer surface K alpha, this friend. It's a 2 2 isogeny. What in this case means is that we get a point of order 2n plus 1 on the Kummer surface. And this, with the formulas that we have, allows us to do a 2n isogeny. Now you might wonder, why not a 2n plus 1 isogeny? And theoretically, you could do a 2n plus 1 isogeny, but actually recovering the codomain is much easier if you have a point of order 4. And so we lose essentially 1 bit, because even for the last 2 isogeny, we still want to have that point of order 4 to get to to quickly learn what the codomain is. And so this structure gives us a 2n to n isogeny on Kummers, and this really matches up to the 2n isogeny on the elliptic curves that would be generated by 4 times this original point P. And this was actually Craig's idea, is that if you have this structure, it also means that in the SIDH square, where Alice computes a very long 2n isogeny, well, we could map all of that down to the Kummers and compute it as a 2n to n isogeny on the Kummer surface. And this works. You can actually show that you could do that and that you match up. But for the SIDH protocol, there's a bit of a difficulty, right? Because Bob needs to do 3 3 isogenies, and then doing 3 3 isogenies needs to do with isogeny of large degree 3 to the power something. And then doing 3 3 isogenies on Kummers is actually getting very tricky and very, very slow. And so it's unlikely that you would beat the original performance there. But this is where our idea comes in, right? So if Costello already gives us these tools to translate a 2n isogeny to Kummer isogenies, where this 2n isogeny is generated by a rational point on your curve, well, then maybe we can also translate this verification of SQIsign, which is a very large degree 2 to the 1000 isogeny, to the Kummer surfaces. So if we try uncompressed signatures, that means that we get a very long isogeny and we cut it up into different blocks of length, let's say 2 to the 70 or so, where this 2 to the 70 is the largest amount of full 2 torsion that is available on your elliptic curve. And then what you can do per smaller isogeny here of degree 2 to the 70, well, this is just a 2 isogeny. And this we can actually translate to this 2 2 isogeny on Kummers. So we map down the starting curve first. E0 we map down to K0. And then we map down all of these kernels that generate the sigmas. So each sigma is generated by a kernel point Ki on EI. And this we can map down. And so we get a kernel point, let's say Ki prime, that generates sigma I prime on each Kummer surface. And so if we give the original Kummer surface K0 and the final Kummer surface Kn and the kernel point, then you can actually verify that this indeed matches up to a 2 to the 1000 isogeny. And all of this on the bottom, this we can do on Kummer surfaces given the tools that we already had, right? So we have the mapping from the curve to the Kummer by Scholten's construction, and then the mapping of the isogeny between these Kummer curves to the isogeny between these Kummers by Costello's work. Okay, so uncompressed signatures are fairly doable. And then we were naive enough to think that maybe we could also do compressed signatures. And then here it turns out that you really need much more tools. And that's really just for compressing these signatures. So what does compressing the signature mean for SQIsign? Well, one of these small blocks, let's say, was a isogeny phi, right, given by some kernel point R. Now, if you could find a deterministic basis for the two torsion, let's say P and Q, then you can express this kernel R, the group generated by R, similarly by the group generated by P plus SQ for the right value of S. And then you just would need to communicate S, which takes F bits, instead of the full point R, or the X value of R. And this really saves a lot of space. And so this is why SQIsign signatures are always compressed, because it's what makes the signatures the smallest in the post-quantum realm. But on the Kummer surface, well, we still have this isogeny given by this single kernel point, by this previous identification that we saw. But now, can we still find a deterministic basis of the two torsion of K? And can we then express R simply in terms of these points? And here we are missing some essential tools, really, to do these kind of protocols on Kummer surfaces. So for one is that you kind of want to check if you have a point on the Kummer surface. Is it coming from the Jacobian above it or from its twist? Because these have the same Kummer surface, but it wasn't really efficient to check the origin here, which is going to be a problem, because if we sample random points on the Kummer and we want to express this point R, we need to know if this point R was actually from the Jacobian or the twist, and also if these points that we're going to express it in are from the Jacobian or the twist. Then we need this sort of point difference, right? So similarly to the genus 1 case, where if you're working with X-only arithmetic, you can only do a scalar multiplication by differential addition. Also on the Kummer surface, you would, given P and Q, need this P minus Q on the Kummer surface. And we couldn't find in the literature yet anybody that was doing that, so we had to develop these sort of tools as well. And then thirdly, actually, how do you find this 2F torsion on K? So given the Kummer surface, what are the points that have 2F torsion? And there are some recent works, and this is where the pairings actually come in, that show actually this is all a bit older as well, but it's used in SIDH and in SQIsign, and in this work where on improving SQIsign, where it shows that there's this very strong connection between these points that have 2F torsion and some pairings. But it wasn't generalized yet to this genus 2 case. And so it was actually very tricky to figure out what is the right interpretation of these pairings that allows us to find these points of 2 to the F torsion. Okay, so then this is what we wanted to do in cryptography, and that's also actually all that I wanted to say about this, is that SQIsign uncompressed is quite easy to do when you have Scholten and Costello's constructions. But then when you want to do something slightly more advanced, like point compression, you immediately need to develop a bunch of tools. Okay, so let's develop a bunch of tools, and for that we will use pairings on Kummers. But to start out with, we'll go to the genus 1 case, because that will be a bit easier, and also because it has one of the coolest facts that I know of, which you can tell all of your friends. Namely that if you have let's say a supersingular curve in Montgomery form, for these primes as we had them in like SIDH or also in SQIsign, then if you want to find a point that has full 2 to the A torsion, like the order is divisible by 2 to the A, it's enough to find a point on your curve where the x coordinate is not a square. Why is that? It is because the image of doubling is given by all of the points xy, where x minus alpha, and x minus 1 over alpha are all square, with alpha a root of the curve equation. And so what it says, if x is not a square, well, it's not going to be in the image of doubling, and so it must have this full 2A torsion. And now you might wonder, why is this theorem true? And this is because the image of doubling is there's a sort of a very natural link to the level 2 reduced Tate pairing. And so rephrasing the theorem says that a point is in the doubling if and only if the Tate pairing for all of the 2 torsion points is trivial. And now here, I'm going to go over this sort of more general theory and actually also state some mistakes that I was making when I was thinking of the Tate pairing, with the hope that maybe you will not make the same mistakes, or maybe you were not making mistakes in the first place, which would be even better. So this is the Tate pairing, let's say, of degree 2, the reduced Tate pairing. And it's a bilinear pairing that on the left takes points, the rational points in your 2 torsion. And on the right, it takes the points on the curve, modulo this image of doubling, and it maps this to mu2. So this roots of unity of degree 2. And then what I was always thinking of is that the second condition is I was always thinking of the second group as sort of just every point on the curve. And yes, it's modulo some equation, so some points, but I was just thinking of them as points on the curve. But actually, that's really the wrong interpretation for what we are going to do. We need to think of these as cosets. So we think of a point plus this whole set 2 times e. How many of those cosets are there? Well, in this case, there will be 4 of them. So, for example, in SQIsign or in SIDH, when we had E super singular, we could think of the whole curve as this group, Z2F times Z2F times some other groups with the cofactor H. And then you had a basis, PQ, for this 2F torsion. And then the cosets are really just defined as, the doubling of E. And then P plus this doubling of E, Q plus the doubling of E, and P plus Q plus the doubling of E. And then actually what the Tate pairing will say, the Tate pairing is a perfect pairing. What that means is that for a point in the doubling, for a point in this doubling, all of these Tate pairings will be 1, right? And this is because it's in this sort of the trivial coset. So that must mean, so if a point has trivial values for all Tate pairings with points in the kernel, in the 2 torsion, it must mean that this point is in this coset infinity plus this doubling of E. This becomes a bit tighter when I define this as a profile. So for a point, in a general point on the curve, what I will define as the profile is the evaluation of the Tate 2 pairing in a fixed basis of the 2 torsion. So I'll just take, and in this case, it would be 2 values, right? So this the 2 torsion we can define by the 2 torsion we can define by a basis of 2 points, and then we would define the profile as the Tate 2 pairing of that point with those 2 basis points. And then what I'm trying to say is that a point is in the doubling if and only if the profile of R is trivial, if this pairing is always 1. And what's particularly interesting is that this profile of R is really telling you in what coset this point R lies, right? So if I know the profile of this point P that I sketched here on the left, or of this point Q, then a point in that profile will have the same, a point in that coset will have the same profile. And so actually computing this profile is quite cheap. It's just 2 Tate pairings, but it really tells me quite a lot. It tells me that this point will have this 2F torsion, and also it will be above a certain 2 torsion point. So I can quite easily, given these correct profiles, find the basis essentially for this 2F torsion, a deterministic basis. So what was my second mistake? I was thinking of this, actually, the Tate-Lichtenbaum pairing as a single value, as 1 kernel point and 1 point on the curve, and some value associated to this. But for these applications, that's not what you want to think of. You want to think of this as an array of values where you evaluate it on all of this kernel of the doubling. And that will give you this profile, and that profile will give you so much information about what you want to do. Now, this will be a bit of an information overload, because now I will go do this for a much more general case, and you might get a bit lost here. But hopefully, when I go back to the genus 2 case, we come back to some fun facts, and it becomes slightly more concrete again. Because what I want to do here is that in 2011, Brian actually defined a generalization of the Tate pairing. For any isogeny, let's say for now, an isogeny between 2 Jacobians, J and J prime, he defined a perfect pairing between the kernel of that isogeny, the rational part, and the co-kernel of its dual. And again, that's the rational part of this. And the co-kernel here is going to be this Jacobian J modulo the image of the dual of phi. Now you might think as an isogeny would be surjective, but I really mean here like you take the rational part of J prime and you take the image of this. And then again, we can define a profile, right? So we take a basis for the kernel of phi, and for a point R, we will define this profile as the evaluation as this array where we define in this basis. Again, as we had before, this profile will determine which coset you end up in this co-kernel. So we can identify actually points in the image of this dual isogeny by having trivial profile. And this is kind of strong, right? Because it means that if I can compute this state pairing, this generalized state pairing, and I find a random point on my Jacobian with a non-trivial generalized state pairing, it means that it's not in the image of this dual. And this will allow us to do quite some cool things later on, actually. And then even stronger, as we said before, these profiles are, these define one-to-one, these cosets. They're consistent on this coset. So we can identify which coset these points belong to just by the profile. And the profile is something for which we just need the kernel. But then we know these cosets are essentially up to the image. So what was the genus 1 example when we phrase it this way? Right, so this really says the same thing. We have this elliptic curve, x minus alpha, x minus 1 over alpha, with 2a being rational. The 2a torsion is rational. And now I call these two torsion points L0, L alpha, and L1 over alpha, alpha bar. And let's say that P0, P alpha, and P alpha bar are the points of order 2 to the f over these Li, where I mean that if you multiply P0 by 2 to the f minus 1, you would get 0, 0, and vice versa for the other ones. Now, what I was saying is that if we took the isogeny, the doubling isogeny, well, the kernel is going to be exactly this, the 2 torsion, which is rational in this case. And the co-kernel is exactly what we had in this previous slide. All of the points modulo the image of this doubling. And now this full profile, I'll do it here for all of the basis points, but you can essentially do it with just 2 of these basis points. With respect to this doubling isogeny, is just this state pairing evaluating L0 in R, L alpha in R, and L bar alpha in R. And so the trivial profile implies that R is in the doubling, but then the profile 1 minus 1 minus 1 implies that R is in this coset P0 plus the doubling. And so it implies that R is above L0. And similarly, the profile minus 1, 1 minus 1 implies R is above L alpha, and minus 1 minus 1, 1 implies that R is above L bar alpha. So that's really strong. We actually can very specifically, we can sample a point and compute the profile and really precisely know where it is positioned in the 2f torsion. Now, actually, this first fact, I didn't really explain why this is true, right? I said that if R has this profile, it implies that R is in this coset P0 and then above L0. So actually what we can do is we can define a different isogeny, phi alpha, which is the one with kernel L alpha. And now here's a fact that you can remember. If you have an isogeny like phi alpha that divides this 2, then we can get the tate pairing with respect to that phi, similarly as the tate pairing with respect to 2. Like computationally, we can do the same things to get that result. So this kernel of phi alpha is now just given by L alpha. And then the co-kernel, actually, this is something that you need to think a bit on during, I don't know, your coffee break or your dinner. What is this co-kernel going to be? So it's going to be the curve E, and points on the curve E, modulo the image of this dual. And if you think about this for long enough, you will realize that points are that are trivial with respect to this pairing. And now the profile really is just one value because our isogeny phi just has a one-dimensional basis. This will imply that this point is above L alpha. And that is this fact that I mentioned before, right? Because you can see that this sort of T phi of alpha is a sort of a sub-profile of that bigger profile T2. And so what are the takeaways here? Well, actually, if you have phi dividing n, the profile is essentially a subprofile of this larger profile Tn. So it gives you more coarse information on the n torsion, so you could say. But it's also cheaper to compute, right? Now, this profile of a point allows us to identify the coset, and in particular is very easy to identify in points that are not in the image of a dual, because you just need one non-trivial pairing there. And that is something that was so strong with this elliptic curve case, because you just needed the x-coordinate to be non-square. But it's also going to be strong in the Jacobian case. So we have E alpha, again, a supersingular curve. And now let's look at these genus 2 friends that we had defined over FP. Now the structure of this Jacobian will be zp plus 1 over 2, zp plus 1 over 2, and then 2 factors z2. Now the image of E alpha under this map that we defined is going to be precisely that first part, this zp plus 1 over 2 times zp plus 1 over 2. And now, if you take a basis for this Jacobian, for some particular reason, what we want to find are points on our Jacobian that are in the image of this E alpha. So generated essentially by a combination of P1 and P2. And we want to find those in there that have this full 2 to the power torsion. So this 2 to the F, you could say. How are we going to do that? Well, in genus 2, you just find the non-trivial profile. But actually in genus 2, this is not going to work, because there are points in J alpha that are not in the doubling, but that still not have full 2 torsion. For example, if you take just P3, just the point P3, it's not in the double of it's not in the double of the Jacobian, right? There's not any point that will map to P3 by doubling. But it does have a non-trivial profile. But it doesn't have order 2 to the F, of course. So instead, what we will do is we compute the profiles of P1 and P2. And then if we find R with either the profile of P1 or the profile of P2, or the product of them, because the Tate pairing is bilinear, then actually we find this R precisely in this image, precisely in that part of the Jacobian that we want to have it. And then not only will it have full 2 torsion, but it will also be in that image of E alpha. Okay, so let's go over that in slightly more, right? So what is this image of doubling? Let's be a bit more concrete about this. We had this order P1, P2, P3, P4. Now the image of doubling is going to be A times this 2 times P1 and B times 2 times P2 for these values of A and B. And this gives us actually 16 cosets, right? So the co-kernel of doubling here is these 16 cosets defined by A times P1, B times P2, C times P3, and D times P4, and A, B, C, D being 0, 0, 1. And this has a similar group structure actually as the 2 torsion. And then these points that I defined before, being in the image of E alpha, are precisely those where in the cosets with C and D equal to 0, which matches up what they said before. It's P1 plus the doubling, or P2 plus the doubling, or P1 plus P2 plus this doubling. Now, here's an advanced trick that I will not go over in much detail, but again, if you have a very long dinner and you solve the first one, here's the advanced trick. Actually, if you think about it, this is again a subprofile. We don't need the full profile T2 of R, but there is a subprofile associated to R that will allow us to identify this already. And this should then, therefore, be associated to some kind of isogeny phi, right? Because these subprofiles come from these isogenies phi that divide the doubling. So there is some isogeny phi where R has a non-trivial profile, and this implies that R is in this image with full 2 torsion. Now the question is, what is this isogeny phi? What is the kernel that generates it? So in practice, why do we want to use this? Why is this related to this SQIsign thing? It's because when we want to compress this point, we wanted to find this deterministic basis. And the points that we wanted to compress were always points with full 2 torsion, because these generate a long isogeny. But then to identify a basis in the right way, we need to deterministically find such points P and Q in order to compress that point. And this is where we use this sort of profiling thing to find that deterministic basis. which means that we really need to compute profiles. We really need to compute 2 Tate pairings on Kummer surfaces. And this is actually not very tricky. This is quite a bit trickier than you might think. There are 3 approaches. The first one uses a lot of theory from theta functions, and I think Gaudry already expressed it in these terms, and otherwise it must have been in a work by Robert, where you can express the pairing in terms of these coordinates, x1, x2, x3, x4, by computing the other theta coordinates and then apply some formulas. Actually, but the second one is actually much better, which is by this recent work by Robert, which was on ePrint just, I think, a few weeks ago, where he shows how you can compute these Tate pairings really easily using essentially the translation via point maps on the Kummer surface. And it's really, it's super nice, and we implemented this and it works very well. The third option that we did is, what if you come up with a much more efficient map to partially map back your points to the Jacobian? Where partially, I mean, we found quite an efficient map to get this A part of the Montgomery for the Mumford representation. And this is all you will need for computing 2 Tate pairings on the Jacobian itself. And for us, this was really the sweet spot, because it allows very, very efficient profiling for points that we sample, because we have this sort of lucky combination of factors going on. So for us, the third method is really, really efficient. So it's, in the end, what we do is we use this map to sample points and very quickly compute a profile, and then we find points with the right profiles in order to compress our points R, or to decompress our points R. Now, I know that this is a bit of an overload of information, probably, and we hope to have the paper out sooner rather than later, so that you can actually read these things in more detail. So for now, I will conclude by just saying that in general, we can do much more on the Kummer. We can, like all of these things that we were doing on the elliptic curve, quite a lot of them we can do on the Kummer. But luckily in Genius 2, this is slightly more complicated. It's a lot of fun to work out how you would do point difference or how you would do pairings on the Kummer. And it really helps also to develop your general sense of what you should be able to do on the Kummer line for an elliptic curve, for example. But then with Scholten's construction, it also allows us to do isogeny-based cryptography on the Kummer over FP. But then doing SQIsign uncompressed is actually quite easy, given the tools that were already out there, the work by Costello and so on. And now our question in our future work really is, can we also do this then faster than doing it over elliptic curves if we use this optimized, parallelized, low-level arithmetic? Then if you want to do compressed SQIsign, it requires it's a lot of fun to develop these techniques, but it does become a bit more complex. And so there we really don't know if this will beat in efficiency, right? Because all of these tools that we develop are quite new and in particularly not heavily optimized. We do our best, but it's likely to improve in the future. And there you really are going to need these pairings. They're great to decompose co-kernels in general, but that applies very concretely to this efficient sampling of points on a Kummer surface. And that's actually all that I wanted to tell you. And I see that actually it's precisely 6 o'clock, so that's pretty good. So if you have any questions, feel free to unmute yourself or to ask them in the chat.
I do. Thank you very much for your talk, Krijn. You stole my line. If anyone has any questions, please feel free to write them in the chat or unmute. Yeah, no, thanks for a great talk. Your slides were really, really cool.
Thanks.
Great. Basically, with all of this now, can you do SQIsign verification completely, like without implementing FP square arithmetic and the elliptic arithmetic? Do you only need these Kummer things, or do you still know?
Yes. There might be 1 or 2 spots left where you need FP2 arithmetic, because sometimes you just need to solve an equation somewhere. But 99% of it will be over FP, on the Kummers.
Okay. Very cool.
Has anyone thought about the attacks instead?
Yeah, we did. And I think Costello also already did. So the idea that there would be a better attack on the Kummers would also translate back to a better attack on the elliptic curve case, right? Because if you could break it on the Kummers, all of these things essentially sort of seem to map back to elliptic curve things. But it does show that there is some kind of a different, more symmetric structure going on these Kummers, and well, maybe with a renewed point of view, it's easier to
surfaces for SIDH already in 2018. So why don't you chime in and say, well, Mace?
I'm sorry, it was a bit of a bad connection for me at this moment.
Great, I couldn't hear. And anyway, thank you a lot, Krijn, for the wonderful talk.
Thanks. Damien has a very good question, which is how do you actually check if a point on the Kummer is on J or on its quadratic twist? And this is where we had this more efficient map to recover the A part of the Mumford representation more efficiently. And this also allows us to compute not the full B part of the Mumford representation, but some partial information on this, essentially the V0 squared, if you've worked with Mumford representations and used the exact same terminology as we did, quite efficiently. And then if this one is a square or not, defines if it's on J or on its quadratic twist.
So I have another question. Can you hear me?
Yep.
Yeah.
Yeah. So what you do is you take the Venn restriction and then you take a two isogeny to work on a Jacobian. But what happens if you stay on the Venn restriction? Is it really necessary to take this two isogeny, or is it just for convenience? Like when you take the two isogeny, I think you have the theta squared model, which is rational, which is maybe not the case if you just take the Venn restriction. Is it what happens?
Yeah, that's a good question, actually. I don't know if you would be able to associate a squared Kummer surface to that Weil restriction. Yeah, it's a good question. We should check that out.
All right. If there are no further questions, thank you so much again, Krijn. And thank you a lot for 25 wonderful episodes. This was, of course, the last talk of this season, but we're hoping to see as many of you as possible in Zurich in just a little over 2 weeks, I think. So yeah, if you're coming to Eurogrid, be sure to go to the Isogeny Club workshop, and yeah, we'll see you all then. Bye bye.